zeros of a polynomial. So zeros is just another word for roots or solutions. And here we're talking about roots and solutions and zeros of a polynomial. Now, if we have a polynomial, p of x, and p of x only has real coefficients, that means that if it has a complex solution or a root, its conjugate will also be a root. So that means if you sub in some complex number z and it equals 0, its conjugate will also equal 0. And this is the conjugate root theorem. So another way to write that is if p of x plus iy equals 0, p of x minus iy will also equal 0. So it's really important to know that p of x only can have real coefficients for this theorem to hold true. If any of the coefficients are imaginary, then this will not work. So an example of a polynomial that it will work is x to the 4 plus x cubed minus 3x squared plus x minus 4. But as soon as we have a complex coefficient, even just one of them, this theorem won't hold true. So we have plus I over here, we have a coefficient that's not real, and this theorem will not hold true. So let's look at have an example of how we can use this. So we want to solve z to the 4 minus z cubed plus 6z squared minus z plus 15 equals 0, given that z equals 1 minus 2i is a root. Now straight away, we can have a look at our polynomial and we recognize that every coefficient is real, which means that roots, if there's any complex roots, they occur in conjugate pairs. And that means that the conjugate of z also has to be a root. So 1 plus 2i has to be a root as well. So we've already got two solutions to this equation and this polynomial, and we're expecting two more solutions. So what we can do now is use our knowledge of sums and products of polynomials to help us solve this equation. So let's let the other two roots equal alpha and beta. So we're expecting two more roots. And let's go ahead and sum all the roots together. So we've got alpha plus beta, and we know two roots already. We know 1 plus 2i is a root, and we know 1 minus 2i is a root, and 1 plus 2i is a root. And the sum of the roots just equals minus b over a, so we get minus 1 over 1. Now the minus 2i and 2i will cancel out, so we just get alpha plus beta plus 2 equals 1, and we get alpha plus beta equals minus 1 as an equation. Now let's go ahead and multiply all the roots together. So let's get an expression for alpha beta times 1 minus 2i and 1 plus 2i. And we know the product of the roots is going to equal e over a, so it's going to be 15 over 1, which is just 15. So let's expand this bracket. So we're going to get 1 times 1, which is 1. 1 times 2i, which is 2i, minus 2i times 1, which is minus 2i. Let's write them out, even though they're going to cancel. And minus 2 times 2 is minus 4, but I times I is I squared, and I squared is minus 1, so we're going to get plus 4. This all is going to equal 15. Yeah, the 2i and the minus 2i will cancel. 1 plus 4 is 5, so we get 5 alpha beta equals 15. And dividing both sides by 5, we get alpha beta equaling 3. Now we just have two simultaneous equations which we can solve. So let's take this one here and say that beta equals minus alpha minus 1, so making beta the subject, and let's sub it into this equation here. So we get alpha times beta, but we know is minus alpha minus 1, and that all equals 3. So we'll go ahead and expand. So we get minus alpha squared minus alpha equals 3. Let's take everything to the right hand side so we can make our alpha squared positive. So we get alpha squared plus alpha plus 3 equals 0. Now we need the quadratic formula to solve this equation for alpha. So we get alpha is going to equal to minus 1 plus or minus the square root of b squared, so 1 squared minus 4 times a times c, which are all those values, over 2 times 1. So we get alpha equal minus 1 plus or minus the square root of 1 minus 12 all over 2. So we get alpha equals minus 1 plus or minus the square root of minus 11 over 2. So we get minus 1 plus or minus I root 11 over 2. And these are actually our values for alpha and beta. So usually when you solve these simultaneous equations for the roots, you don't have to go sub it back in because you get both of your answers in one go. So that means we can just tidy this up. We can write it as minus 1 over 2 plus or minus root 11 over 2i. And because we have a complex number as a solution, we also have the conjugate as a solution. So because all the coefficients were real. So it means the final solutions for z is that z equals 1 minus 2i, 1 plus 2i, minus a half plus root 11 over 2i, and minus a half minus root 11 over 2i.